And welcome there, calculus folks. The warm-up here, hopefully you've tried it, is back to implicit differentiation. Today we start a couple of days on a topic in calculus called related rates, and we'll see that it kind of goes with implicit differentiation. So there was a warm-up question there, and hopefully it wasn't too bad. Remember, anytime we have an dependent function, y is implicitly defined in this formula, um, then we have to use a chain rule, right? This is like the y is an inside function, and so when we take the derivative, the 2 comes down, the inside thing is the y, but then since y itself is a function, then we have to take the derivative of it. And again, notice that I'm using Liveness notation. If you wrote y prime there, yeah, you're fine here. But I'm using Liveness notation on purpose because we'll see soon that that's what we need for related rates. This is one of the topics where we really do need Liveness notation. And then hopefully you got that, and then you factor out the dy by dx or y prime, however you did that. Hopefully I haven't made an arithmetic error, and you get that expression. What I want to mention before I go on with the other warm-up questions here is, what would it be like if I took the derivative with respect to some other variable? Like, for instance, in the optimization questions, the 2 ships passing in the night question, we saw that x was a function of t, something like this, I think. And you'll have to write this down, but both of these, the x and the y, were also functions themselves. So then I could take the derivative of this expression with respect to a different independent variable. I could take the derivative with respect, with respect to t, say. Right? Take the derivative of this expression with respect to t. And in fact, we did that in our optimization questions at time, right? So what would that look like? Well, everything's a chain rule then. I'd have 2y and then derivative of y with respect to the independent variable t, and then I'd have a product rule where the derivative of x is just dx dt, right? Because we said x is a function of t. Derivative of the first, write down the second, plus write down the first derivative of the second with respect to the independent variable t, plus another chain rule. I say, well, hang on, Restall, how are we solving for d? Well, we're not really. What we've got is we've got an expression that involves both the functions x and y that are implicitly defined, and also their derivatives. Their derivatives with respect to some other independent variable. T in this case was time, and we'll see that in today's stuff, often time is the independent variable that we're interested. T is the independent variable, usually for today's stuff, instead of x. X was a function just like y was. All right, dandy. Okay, there's more warm-up questions. The position of an object after t minutes is given by s to t. Explain briefly what each represents or means. So ds by dt, well, it's the first derivative. Well, no. If this is the position, then what's a? A then is the change in position over an amount of time with respect to time t. Well, what else? You could have also said that this is the velocity, right? This is the velocity. And I would have been okay with that. What does this statement say? Well, remember, s is the position. This is, say, at t equals 5. Time is 5. The position is, well, what does that mean? This here means the position is minus 10. We'll say left. It could be down, but left, right. The object was left 10 units. Okay. What about s prime at 5? At time equals t. What does negative first derivative mean? It means it's moving left. The velocity is left. The object's position was changing left, moving left. At 10 units, maybe it's meters, centimeters, whatever, per minute or per second. Oh, minutes. At 10 units per minute. Okay, what is the second derivative? That means at time t, it was accelerating left or being pulled left. Usually we say accelerating. The acceleration left at, left by 10 units per unit, right? This per minute would be 10 units per minute squared. That's the acceleration. And so that means it was left, being pulled left, and accelerating left. Remember, when the two are together like this, if it's moving left and being pulled left, we can say that it's actually speeding up. When the acceleration and the velocity are in the same direction, that it's speeding up. Okay, great. Well, what's the big whoop? Why are we talking about this? Well, it's nice review for one, but it also leads into this is going to be the big difficult thing for today's stuff. After 15 minutes, the object is 25 meters to the right. 25 meters to the right. That's talking about position, isn't it? So this is saying after 15 minutes, the object is 25 meters right. Position. That's it. So what's B? After 4 minutes, so this is t equals 4, the object is moving left at a rate of 5 meters per minute. Moving left. So that means the first derivative, the velocity, after 4 minutes, is moving left at 5 meters per minute. Right? Left is negative. By the way, I want to sprinkle in the Liveness notation. So that means the position is changing with respect to time when time equals 4. When time equals 4, the change in position is negative 10. Okay, so that means the ds by dt, that line means when t equals 4, and that's the value. So these two are equivalent statements. This is what we're going to get used to today more and more, okay? Hopefully you're getting more and more comfortable. After 15 minutes, the distance is increasing at a rate of 12 meters a minute to the right. The object's distance is increasing. The distance is increasing at a rate. So that's going to be then the distance is increasing at a rate at time equals 15 minutes of 12 meters per minute. This isn't an acceleration. This is also a velocity. This is also this. Oops. And I can fill in because I know what the time is. The time was 15. Okay. The distance is increasing, not the velocity is increasing. The distance is increasing. Dandy. Let's go on and talk about these symbols, by the way, they're going to be important in today's lesson. So it's called related rate. Solve problems associated with derivatives that arise from real life applications. So a spherical balloon is being filled with helium at a rate of 8 centimeters cubed each second. At what rate is its radius increasing when the radius is 12 centimeters? So there's two questions. I'm going to start with A. And I'm going to use the grass method here. What am I given? I'm given this 8 centimeters each second. What is that? What is this given? What is this given here? At a rate, the volume is changing at a rate of 8 centimeters each second. Being filled means it's positive, right? The volume is increasing. Volume increasing. at 8 centimeters cubed per second. Well, what is that in symbols? That's the volume, the change in volume with respect to time is equal to 8. And that's not at a specific point. That's always true. Okay, dandy. What else are we given? Or what's required? We want to find at what rate is its radius increasing. What rate is the radius increasing? Well, that's dr by dt. dr by dt when the radius is 12. All right, well, so how do we do this? This isn't an optimization question. I'm not trying to find the maximum volume or the minimum cost or anything like that. I just want to find out this value when r equals 12. So you could almost think that this might be a given up here, r equals 12. Sure. So now how do we handle this? What's the analysis? Well, at some point, I need to find an equation. We need an equation to relate the given and the required. Given and required. Well, what does it? Well, the volume of a sphere, right? And of course, everyone knows what the volume of a sphere is. It's 4 pi r cubed. 4 pi r cubed over 3, rather. That's the volume of a sphere. If you had to look that up once, that's fine. It's going to come up once in a while, so you'll remember, I hope. Well, what's going on? I know that r is 12. I could calculate the volume here, but really what I need is dr by dt. I need the rate at which the radius is increasing. Well, I might be thinking about taking the derivative. Right? Let's see what happens if I take the derivative. Because when I take the derivative with respect to time, on the right-hand side, I'll probably end up with dr by dt. So watch what happens. On the left-hand side, dv by dt. On the right-hand side, notice that this piece right in here, this is all number part. So I could think of that as the number part out front. And then when I take the derivative, the 3 comes down, and I got 12 pi over 3 is the number part. R squared, but remember, R is changing. It's a function of time as well, right? And in fact, that's the inside thing. I need to take the derivative of the inside thing, and there's my unknown, right? That's what I want to find right there. So that means I must know everything else. Well, dv by dt, that was 8, right? So sub in for other stuff. There, we identified our unknown, sub in for other variables. We're going to run into a little bit of a trap here, but this is 8 there. That's all number. Why don't I tidy that up now? That's 4. What's the radius, though? I don't, oh, the radius is 12, isn't it? The radius is 12. Fine. And now dr by dt, all I have to do is get all these other numbers away from this, and I'm going to be able to do that no problem. So this is 8 over 4 pi. 12 squared is 144. A little arithmetic here, and I'll have this exactly for you in just a second. What do I got? I got 8 over 536 pi. That's how much the radius is changing. So the radius, when this balloon is being filled at 8 centimeters a second, the radius is increasing by that rate, which, by the way, is about 0.0044 centimeters per second, right? Rate, the radius is in centimeters, time is in seconds, centimeters per second. So this was my solution starting right about there. Here's my statement. So when, I don't know what the time was. I don't know how many seconds had gone by or anything like that, but I know when the radius was 12 centimeters. It was increasing by 0.0044 centimeters per second. That's a related rate. Dandy. Okay, we got example 2 and 3 still to do. I'm gonna pick those up in part 2. We'll see. This is the type of thing we're doing. We're, take a derivative and just substitute in for the known values, solve for the one that we need. And we'll see a couple more examples in part 2.